Good afternoon, dear colleagues. My name is Pavel Karpyshev. I am a PhD student at the Skolkovo Institute of Science and Technology, and today I am going to present a paper called MuCaSLAM, CNN-based RAM quality assessment for mobile robot with omnidirectional visual SLAM. The area of e-commerce is growing at an astonishing rate and is predicted to grow up to more than 2.5 trillion euros by the year 2023. This growth has inevitably led to advances in all surrounding areas, including the markets of good delivery. And in that area, one of the most important parts is the so-called last mile delivery, that is, the coverage of the distance between the nearest shop or warehouse directly to the customer. The solution to the problem of automated last mile delivery would be the use of autonomous ground vehicles, AGVs. Such solutions have already proven effective and cost-efficient and have created a huge demand on the market. Localization and mapping algorithms are an essential part of every autonomous robot and are often combined into one module, simultaneous localization and mapping, or SLAM. State-of-the-art SLAM algorithms are able to utilize a wide variety of sensors, from inexpensive rolling shutter cameras to LiDARs and 3D cameras of different types. The AGVs that are currently being developed or tested mostly utilize LiDARs for the SLAM task, and that is dictated by the robustness and versatility of these sensors. The visual SLAM algorithms utilize the information from visual sensors, for example, global and rolling shutter cameras, for the localization and mapping. Such approaches use the data from much cheaper sensors and thus make the systems based on them more cost-effective. Moreover, the cameras installed on the robot can be used for multiple purposes apart from localization, for example, object and human detection, thus further decreasing the required set of hardware and the overall system cost. However, the use of low-cost visual sensors has its own drawbacks. Cameras are much less robust to changes in illumination and weather conditions and show overall worse results compared to LiDARs, in the scope of the SLAM problem. Furthermore, the field of view of the cameras is limited, thus making such systems even more dependent on the quality of data. We propose an evaluating approach that increases the robustness and computational efficiency of visual SLAM algorithms in multi-camera setups. For that, we supplement the ORB-SLAM 2 state-of-the-art visual SLAM algorithm with a pre-processing module that consists of the classification neural network. The aim of the network is to determine the quality of input images, that is, the conjectural number of ORB features that the ORB-SLAM 2 algorithm will base its estimation on. After the network predictions, the best resulting images are transferred into the SLAM pipeline. For the proposed study, we have used the HermesBot platform developed for the research in the area of autonomous ground robotics. The platform consists of a base with 6 motor wheels equipped with encoders, a metal frame with a number of sensors installed on it, including, among others, 6 rolling shutter Raspberry No IR version 2.18 megapixel cameras. The cameras are installed on both sides of the robot facing sideways and at the angle of 45 degrees to the sides. Prior to the dataset collection, all cameras were calibrated using a chessboard pattern, and the transformation matrices for each camera were calculated based on their location on the robot. The platform is controlled using a tandem of 2 computational units, an Intel NUC computer featuring an Intel Core i7 processor for general control and data handling, and an NVIDIA Jackson Xavier module for image processing. The neural network module is installed on both the NUC and NVIDIA Xavier, with the former utilizing CPU for computation and the latter using GPU. This was done in order to evaluate the performance of the proposed approach on both CPU and GPU and compare it with the traditional ORB-SLAM 2 pipeline and the ORB feature extractor and matcher that can only operate on a CPU. The scheme of our system's software, architecture, and general data processing pipeline is depicted in this slide. AGX Xavier, Intel NUC, and cameras share a common ROS environment. Each camera posts its frames into a corresponding ROS image topic. The Xavier listens to new images and fits a batch of them into the neural network. Each batch consists of 6 images, 1 image per camera. The network predicts the probability for an image to have enough features for the correct operation of ORB-SLAM 2, and the best resulting image is transferred to the SLAM pipeline. We used the pre-trained ResNet 18 convolutional part as the backbone, and after its average pooling layer, we added a fully connected head. The fully connected parts consists of 2 hidden layers with 512 neurons with ReLU activation, and 1 final layer with 2 neurons with softmax activation. Each neuron returns the network confidence on the image relating to the corresponding class. The network is trained to the classification task using Adam optimizer with learning rate of 0.001, beta 1 of 0.9, and beta 2 of 0.999. We trained both the pre-trained ResNet 18 backbone and the head during 8 epochs with the batch size of 128 images on our dataset. For the training and evaluation of the proposed approach, we have collected a dataset of visual data in Skoltech campus. The dataset composes of typical indoor scenes including open spaces, corridors, plain walls, empty rooms, as well as various kinds of static and dynamic obstacles like chairs, tables, moving people, etc. Thanks to the camera position setup and the chosen dataset location, each video sequence consists of both feature-rich and feature-poor images depicting typical data collected on an indoor ground robot trajectory. The dataset consists of 3 sequences recorded in different areas of the building and of different length. After the dataset collection, all frames were processed using the orb feature extractor and matcher, and only the good features that were matched with the subsequent frame were used for network training and evaluation. To determine whether the feature is good, we evaluated the matched key point descriptors by compiling a fundamental matrix for each pair of consecutive images. This allowed us to train and evaluate the neural network only on key points that were successfully matched with the subsequent frame and thus ensured the correct operation of OrbSLAM 2. An example of the good features histogram is depicted in the slide. The histogram shows that the number of features varies from 0 to 1000, with the mean around 400 features per image and the median at about 500. We use the threshold to divide images into 2 classes. Images with number of good features is higher than the threshold are labeled as good ones, otherwise as bad. Based on the data distribution, we chose the threshold as 450 features. In order to evaluate the proposed approach, 3 sets of experiments were carried out. During the first experiment, we trained the neural networks on sequences 2 and 3 in order to validate their performance on sequence 1. That does not intersect its trajectory with the subsequences for training. To evaluate the efficiency of the classifier, we used the classification accuracy score, that is the amount of true positive and negative predictions with respect to the overall number of neural network predictions, and F1 score, that is a harmonic mean of precision and recall, where the best value is 1 and the worst score is 0. The table in the slide demonstrates both the high level of accuracy and F1 score on each camera on validation sequence 1. Among all cameras, the average precision is 0.926 and the average F1 score is 0.924. Thus, the proposed architecture is able to robustly predict the camera frames that are most suitable to be fed into the OrbSLAM algorithm, and the high number of potentially matched orb features is 90% guaranteed according to the results in the table. During the second experiment, the trained neural network was launched on each camera of sequence 1 and the information about the amount of good potentially matched features was obtained. The best camera with the highest values of good features at each timestamp was chosen based on the neural network predictions after exponential smoothing. So we have obtained a sequence of camera numbers with the best quality to use in the SLAM pipeline during the operation. Launching the extraction and matching of all features on the obtained sequence with the images from cameras chosen by the neural network gave us promising results, depicted in the figure. By switching to the camera that was predicted to have the highest number of good features, we obtained a new sequence, depicted ours in the figure, with an average of 691 features per frame. Another generated sequence in the figure is mean, that is the mean number of good features in all 6 cameras, averaging at only 386. The results confirm that the proposed approach works well and that sufficient number of features can be maintained during the operation using the camera switches based on the neural network predictions. In order to validate the performance of our system, we evaluate the speed of our neural network on the Core i7 CPU and GTX 1070 GPU. The experiment has 2 parts. The first one was devoted to find out whether the processing of orb extractor plus matcher is less efficient than the neural network approach of figuring out the camera feature goodness. The experiments have shown that one iteration over 6 images using the traditional orb matcher takes 120 milliseconds, and the same iteration of the neural networks takes 10 milliseconds and 2.7 milliseconds when run on CPU and GPU respectively. According to the experimental results, our approach is significantly faster than ORB feature matching, approximately 12 times on the CPU and approximately 50 times on the GPU. In the course of the second experiment, we compare the performance of ORB-SLAM 2 running on one camera and on 6 cameras, ORB-SLAM 2 using our neural network on current and the 5 remaining cameras, and one ORB-SLAM 2 with an estimate of the number of ORB features matches on current and 5 remaining cameras. ORB-SLAM 2 and matching processes were launched on CPU throughout the whole experiment, since its architecture makes it unable to utilize GPU. The table shows that the use of a neural network in the system will increase the ORB-SLAM 2 computational time by only 20% if running on a CPU and by 5% if running on a GPU. The use of a standard feature matching algorithm increases the processing time almost 3.5 times. Thus, on a mobile platform with limited computational resources, it would not allow ORB-SLAM 2 to operate in real time. On the testing hardware, the performance of even two ORB-SLAM 2 pipelines with our neural network has achieved near real-time operation. Therefore, it may be possible to use the two best resulting cameras instead of one, further increasing the robustness and reliability of the system. To sum up, in this work we presented an approach to improving the computational efficiency and robustness of visual SLAM algorithms on mobile robots with multi-camera setups. This was achieved using a neural network based on ResNet 18. This network makes a prediction about whether the image contains enough ORB features that can be matched with subsequent frames. The average number of good features on the data proposed by the neural network amounted to 691, as opposed to an average of 386 among all frames on all cameras. This value and the absence of feature level drop make it possible to ensure the reliable operation of the ORB-SLAM 2 algorithm even if images from most cameras do not contain a sufficient amount of key points. The computational complexity increase was only 5% when adding our solution to the SLAM pipeline on 6 cameras. The iteration time using the proposed neural network was only 2.7 milliseconds when using the GPU and 10 milliseconds on the CPU. This proves that our solution can increase the robustness of visual SLAM and multi-camera setups without a significant decrease in performance. Our future work will be devoted to implementing the camera switching pipeline into existing visual SLAM approaches, as well as ensuring the smoothness of transitions between them. The SLAM initialization time will be taken into account as well. The performance of the proposed approach will be further compared with state-of-the-art visual SLAM approaches and depicted in further publications.